Okay. Assalamualaikum and uh, good afternoon. So today we cover mechanical energy balance. So in chemical process unit, so this is based on two books. I'm using elementary and the basic principle of beginning. Book is available in elite. So for elementary chemical engineering, we refer to page 375. So in chemical processes such as vector, distillation, column, evaporative heat exchanger. What? So you may refer to page 370. So another important class of population is one for which the opposite is true. Heat flow and internal energy changes are secondary and important to kinetic and potential energy changes in shaft fluid. Most of the operation involve the flow of fluid to, from, and between the tanks, reservoir, well, and process unit. So counting for energy such processes is most convenient done with the mechanical energy balance. So to derive the equation, you start with the equation 7.7-1. So letting M one is mass flow rate and V the specific volume of the liquid. So if V is replaced by 1 equal to rho, where rho is the liquid density, then the open system energy balance 7.4-12 may be written as 7.7-1. So the shaft work WS is the work done on the fluid by moving elements in the process line. So in many cases, only slight amount of heat are transferred to or from the surroundings. There is little change in temperature from inlet to outlet and no phase changes or action occur. Even under this circumstance, some kinetic or potential energy is always converted to thermal energy as a result of friction due to the movement of the system. So when the quantity U over M always has a positive component, termed the friction loss, it is given the symbol F. Equation 7.7-1 may therefore be written as 7.7-2. So 7.7-2 is referred to as the mechanical energy balance. So this equation. Once again, it is valid for steady state flow of an incompressible fluid. So a simplified form of the mechanical energy balance is obtained For frictionless process, F is approximately 0, in which no shaft work is performed, Ws equal to 0. So equation 7.7 is called the Bernoulli equation. So Bernoulli equation, you see, there are no term for F, meaning it's a friction process, and there are 0 shaft work. So mechanical energy balance applied to steady state case, in which heat transfer and thermal changes are not important. So this is the mechanical energy balance. This is the Bernoulli equation. So this is the mechanical balance with friction loss. You notice the changes in the equation, but it's the same. So this is based on book, the basic basic principle in what's it? Basic principle in chemical engineering. You see the equation, but the meaning is the same. So instead of F, it's EV, same. Yeah, everything is the same. V, here is U, G, same, H is same. Okay. To example 1, okay, refer to it. Page. This is basic chemical engineering books. Refer to page. Boy. Oh, okay. Refer to section 8, 5.3, meaning chapter 8, section 5.3. Yeah. The first example is example 8.16. Calculation of the power needed to pump water in an open steady state system. So the problem statement, water is pumped from a well, figure E 8.16, in which the water level is a constant 20 feet below the ground level. The water is discharged into a level pipe that is 5 feet above the ground at a rate of 0.5 feet cube per second. Assume that negligible heat transfer occurs from the water during its flow. Calculate the electric power required by the pump if it is 100% efficient. You can neglect friction in the pipe and the pump. Okay. So based on this equation, this is the equation for without the friction. Right. But it says here neglect the friction, so there are no F. In this case, for this book, there is no value for EV. So EV stands for uh, frictional loss. Frictional loss, yes. It's the same thing. Frictional loss and What are they? Friction loss. F. Let's pick as the system the pipe from the water level in the well to the place where the water that exits is at 5 feet above the ground, so that the pump is included. Let's simplify equation 8.22. So equation 8.22 is referred to if you refer to the book, it's ya buku ya. So this is 8.22. So 8.22 is similar to 7.7-2. 7.7-2 except for the EV or friction loss. Because this is a steady state system. Because this is a steady state system, and the pump diameter appears to be the same for both the inlet and the exit. So delta KE equal to 0. KE refer to kinetic energy. And then also the pressure at the exit is equal to the pressure at the inlet. After this simplification, equation 8.22 become W over M, this equation, equal to G delta H. If you refer to basic, elementary chemical engineering book, it's Z, G delta Z. It's the same thing. Refer to height. So this is the M or flow rate, mass flow rate. Then we have density, gravity, acceleration, delta H or height. Then we have this gravitational constant. It's 32.174. Simplify to 32.2. Then the unit conversion. So W equal to 1.42 HP. Because this analysis neglected friction and the efficiency of the pump, it represents an estimate of the required pump size that is less than the actual size required. So exercise 1. So assume that you want to siphon gasoline out of the gas tank using a hose with 0.5-inch diameter inside the meter. Determine the flow rate of gasoline in gallon per minute based on the arrangement shown in figure 8.17. Neglecting the friction between the gasoline and the hose. So simplifying equation 8.22. So we have this equation. The pressure at the entrance and exit for this system will both be atmospheric, so the flow work should be 0. No work is applied to the system, therefore the mechanical energy equation reduced to 1 over 2 delta V square, just the kinetic, plus G delta H. Solving for the exit velocity, assuming the entrance velocity is 0, we have v equal to square root 2g delta h. So in this book, it's using what is it? American, right? Yeah, American unit. If you refer to another book, the elementary is using an SI unit. So you see the G here this is the gravity acceleration. In SI, it's 9.81 meter per second. This is 2 feet. Then the velocity is 11.35 feet per second. So finally convert the average velocity into the volumetric flow rate using the cross-sectional area. So Q equal to AV equal to pi. So A here refer to the pipe, cross-sectional area of the pipe. So the pipe inside diameter is 0.5 inch inside ID. So pi r square. Yeah. This is diameter, so you need to divide by 2. That's why it's 4. Then we have this value in 11.35 feet per second. Okay. So this is a unit conversion, then unit conversion. Is to feet cube to gallon minute per 2 second. So we have 6.947 gallon per minute. So if it in SI unit is the same. So example 2. So consider the hydroelectric system shown in figure 8.18. The Hoover Dam has a power capacity of 2080 megawatt of electricity. The current water level at the dam is 1070 feet. Assuming 100% efficiency for the hydroelectric power at Hoover Dam. Calculate the flow of water in kg per second and gallon per minute through this hydroelectric process. So water transfer from here to the turbine to the downstream outlet. So your task is to calculate the flow rate of water in kg per second and gallon per minute. So first of all, goes to the chemical equation, simplifying the equation. To 7.7 is 2 of equation F.22 is the same. So in this case, there are no friction. Then simplifying this equation, actually you get this W over M equal to G delta H. So solving for M and making the proper unit conversion yield how much? 6.503 time per 10 to the power 5 kg per second, or 1.031 times 10 to the 7 GPM. So here this is the power. The height, h or z. This is the gravity, right? Unit conversion. This is unit conversion. Unit conversion. So exercise 2. Determine the flow rate from tank A to tank B for the system shown in figure 8.19 in GPM. Assume that the fluid being pumped is water and 25 horsepower pump is used. The pipe in this system has a 2 inches inside diameter. Neglect the friction in the pipe and the pump. So simplifying the mechanical energy balance equation. So the flow work should be 0, therefore the mechanical energy balance reduced to W over M equal to 1 over 2 delta V square plus G delta H. So note that M and V are both depend on the flow rate Q between the tank. So M equal to Q rho and V equal to Q over A, where A is the cross-sectional area of the pipe between the tank. Therefore, the previous equation become, okay, you substitute it. So W over Q rho, Q is the flow rate, rho is the density. Then Q square over A square, that one is referred to the velocity here. So flow rate divided by cross-sectional area equal to velocity. Then G delta H. This is a cubic equation in Q. Yes, correct. You need to use MATLAB or Python to solve it, but we must be careful with the unit for this problem. Not that the term, not that each term should have unit of feet square per second square to match the unit of G delta H. Okay, so WHP, this is the unit for density, flow rate, unit conversion. Wait, sorry. This is referred to the gravitational constant. But for SI unit, you don't have to use gravitational constant. Yeah, you may refer to that basic. So the elementary chemical engineering book. So far the example, they didn't use gravitational constant, but in American unit here, yeah, it's using this. gravitational constant. So the purpose they do it is to make sure the unit is equivalent to G delta H. Okay, this is for 2Q2 feet. Oh yeah, of 6 divided by S. This is for this term. Okay, it's equal to feet cube feet square per second. So from here where W is in horsepower, Q in feet cube. Okay. This is a single nonlinear equation. We use the built-in function in MATLAB. So because the equation asks you to determine Q. Yeah. How much is Q? So the answer is based on this book. So the answer is 0.3151. Therefore, the flow rate through the system is considered to be 0.3151, or Q equal to 0.3151 feet cube per second. Yeah. But nowadays the calculator is very good. So what you need to do is just plug in the value 71710 multiply with 0.25 HP divided by 62.4 pound mass per feet cube, which is the the um, the, the density, sorry. Yes, then equal to Q square divided by area square. The system, sorry, the question have given you the diameter here. So this is the cross-sectional area. Multiply with yeah, 144. Okay, the unit conversion for feet square to inch square plus 32.2 feet per second square, which is the gravity in in feet per second square. Sorry. Yes, gravity acceleration. Multiply with delta H, which is the 25. So the term is Q2, so Q square and Q. If you simplify it, you can just solve it uh, using a calculator. So, so for this basic principle of chemical engineering book, there are extra section. If you refer to the elementary, This is the elementary chemical processes book. It's top until here. Yeah, example 7.7-3 hydraulic power generation. For the basic principle in chemical engineering, there are extra section about energy variant for special cases. So the previous section addressed the most common type of variant encounter in the process industry. Nevertheless, sometimes you will encounter a system that does not fit into one of the three categories. And in that case, you should apply the energy balance, general energy balance equation. Delta U total of the Q plus W minus E CONV. So delta U here refer to the internal energy as well as kinetic and potential energy of the material in the system of interest, and delta E CONV, and then the enthalpy as well as kinetic and energy of the material living in the system. Each of the term in the energy balance has been explicitly defined and demonstrated in the previous section. So for the unsteady state open process, steam at uh, steam at 250 degrees C saturated, which is used to preheat the fermentation broth, enters the steam chest. The steam is segregated from the minus solution in the preheater and is completely condensed in the steam chest. The rate of the heat loss from the surrounding is 1.5 kilojoule per second. The material to be heated, which enter at 25 degrees C, flows into the process vessel, which initially is at 20 degrees C. If 150 kg of furnace with an average heat capacity of Cp equal to 3.26 joule per gram Kelvin flows into the process per hour, how many kilograms of steam are needed for per hour? So this is based on SI unit. So this is the diagram. So 150 biomass solution per hour. So 50 kg solution per hour goes into the steam chest. Then we have the steam going in at 250, which is saturated steam. Then going out as a saturated condensate at 250 degrees C, set temperature. Q loss is negative 1.5 kilojoule per second. So step 1 to 4 is figure E at when to 1, this figure. Okay. So the material balance for the steam is in M in equal to M out equal to M, and M is an unknown because it's asking, sorry, how much steam are needed per hour. So meaning it's a mass flow rate. So the material balance for a member station is also simple. What flow in stay in the system and she no biomass was in the system in the vessel and at the end of 1 hour 150 kg of solution existed in the vessel. As a result, one or more unknown are associated with the biomass solution. Next, let's examine the energy balance for the system to ascertain if the balance can be used to solve for M. Okay. General energy balance is delta U total equal to Q plus W minus E C or NV convert. Let's simplify the energy balance. So the process is not infinite. So delta U is not equal to 0. U refers to internal energy. We can safely assume that delta KE is 0. Delta PE inside the system for the flow is 0. Then the work done on the system, so W equal to 0. So consequently, equation A, this equation, turn to delta U equal to Q minus delta M HH referred to enthalpy. So delta U can be calculated from just the change instead of the biomass solution and does not include the water in the stream chest because we will assume that there was no water or steam in the steam chest at the start of the hour and none in the steam chest at the end of the hour. So 150 kg, then we have U final minus 0 kg U initial. Equal to negative 1.5 joule per second. It is Q loss. Unit conversion here. Then M steam, this is the enthalpy. Choose a reference temperature either 0 or 20 degrees C. The P reference is 1 by assumption. Pick T reference equal to 20 degrees C. Because this is the initial temperature of the steam chest. Yeah. So P, okay, delta U equal to delta H. So U final equal to 3.26 kilojoule per kg degree C. That one is the CP. Multiply with then we get 81.5 kilojoule per kilogram. Another one is U is 0. Why? Because the reference temperature is 20 degrees C. So in this case, 20 degrees C is the initial state of the steam chest. Or the process vessel or steam chest. Sorry. This is referred to steam chest or method to be heated. Okay, that one is referred to the process process vessel because the biomass solution and the steam chest is not mixed. Yeah. Then H2 minus H1 equal to delta H condensation of steam equal to negative delta H vaporization at 250 degrees C, which is equal to negative 1701 kilojoule per kilogram. Reduce this value into equation C. This equation. So 12,225. Equal to 150 multiply with the 81.5, you get 12,225. Then this term here, sorry, this term here. So this is where you get the 150 at 1.5. You get 12,225. 3600 multiply with negative 1.5, you get 5400 minus m multiply with this value. Then the flow rate of steam is 10.4 kg per hour. So heat of vaporization at 250 degrees C, that one you need to refer to steam paper at 150 degrees C. Exercise 3, exercise 4, okay. Okay, you should try the exercise 2 exercise. So this exercise is based on book elementary chemical processes. Yeah, elementary chemical processes. Thank you.